Hello everyone, welcome back to another video, and in today's video we have a complicated complicated network of pipes, and we want to calculate the water flows through each pipe that we have, and we want to find the net flows in each of our nodes for our system. And our source node is going to be node 0, and our sink node will be node 4. And all the elevations of the pipes will be 0 meters except for node 0, which is at 30 meters. Node 4 will have a pressure of 0 pascals, and node 0 will have a pressure of 200,000 pascals. And the diameter of all the pipes is 0.1 meters with a relative roughness of 0.001. And down here we have an array that kind of shows our pipe system. So the first column is our from nodes, and they're connected to the two nodes, and then the lengths of the pipes is the third column, and the last column is the K values for all of the pipes. And the K values are just the heating due to friction due to certain fittings in the pipes, like valves or turns and things like that. So to begin, let me just go ahead and draw our piping network. So we have node 0, node 1, node 2, node 3, and node 4. And node 0 will be connected, node 0 will be connected to node 1, node 1 will be connected to node 2, node 1 and 2 will be connected, nodes 1 and 3 will be connected, nodes 2 and 4 will be connected, and finally nodes 3 and 4 will be connected. And as I said, all these pipes have a certain length and a K value, and node 0 will be at 30 meters, and the rest of them will be at 0 meters. So surprisingly, with just the information we're given, we are able to calculate the flows. And to do this, we want to look at Bernoulli's equation. And Bernoulli's equation is going to be our change in pressure over rho plus our change in altitude over g. And we're going to be ignoring our changes in velocity because it will be 0, and that is going to equal our negative heating due to friction. I can't draw the fancy F, sadly. I wish I could. And to start, let me just go ahead and divide both sides by g. And our heating due to friction is going to be equal to our K values plus 4 times our heating factor. Is that what it's called? Friction factor. And then times L over D, and then all that will be times V, or velocity squared, over 2. Alright, so to begin, this right here is going to be our delta head. And if we want to find the flows, we need to find this velocity. So we're going to need to solve for our delta head, and we know K, we know L, we know D, we know G. So we also need to solve for our friction factor, and that is where we will begin. So let's go on over to our good friend Python, and we'll start, and we'll start by importing numpy as np. And to find our friction factor, we're going to define a function that is going to call for Reynolds number and the relative roughness. And to find our friction factor, we'll be using Churchill's equation for the friction factor. So it's going to, this is the equation, F will be equal to this, and our A and B, we will go to that. So to solve this, we just need to just put in the equations for A and B, and we want to return our value for F. So let's just go ahead and do that. So A is going to be equal to 2.457 times the natural log of 7, that's a T, 7 over Reynolds number. That will be raised to the 0.9 plus 0.27 times our heating coefficient, and this, or not heating, our relative roughness, and this is going to be raised to the negative first, and all this will be raised to the 16th. And for B is going to be equal to 37530 over Reynolds number raised to the 16th. 37530 over RE raised to the 16th, and we can return our values for F. So 2 times 8 over Reynolds number to the 12th plus A plus B raised to the negative 1.5, and all this will be raised to the 1/12. Yes. Okay. Shift enter. Alright, and if we want to check to see if that's right, we can plug in a value for our Reynolds number, and let's put 1 for our relative roughness for now. Well, that's not right, because we can compare it to 16 over 100. So it should be 0.16. So let's see what we did wrong here. 2, 4, 5, 7, 0.9. .9 plus 0.27 times ED. Okay, here's probably have too many parentheses now. 1, 2, 1. There, okay, so I just messed up. Alright, so that is our friction factor solved. So the next thing I want to find is our delta head given a flow rate. So to find our delta head, we need to find our negative F over G, and negative F equals this. So if we just put that over G, that will solve for our delta head. And we're giving a flow rate. So flow rate, so our velocity, is going to be equal to our flow rate over our area. So that's going to equal our flow rate over pi times d squared over 4. Okay, so let's go ahead and make a function for that. So d head, or delta head, calling for our flow rate. We need a length in our pipe, a diameter, a K value, and our relative roughness. And with that, we need to solve for V first. So V is going to be equal to Q over pi times D squared over 4. And we need to solve for a Reynolds number, and that's going to be equal to rho, so the density, times the velocity times the diameter over the viscosity, mu. So let's go ahead and define some of these variables that we know. So G is going to be 9.81. Our diameter will be 0.1. Our relative roughness, 0.001. Rho, we're working with water, so it's going to be 1e to the third. And our mu is going to be the viscosity of water, so 1e to the negative third. And then we want to return that side of the equation we just solved. So negative k plus 4 times our friction factor times L over D, and then that will be multiplied by V squared over 2 over G. So let's go ahead and call that, make sure it's working. So we'll say a flow of 1 cubic meters per second, a length of 5, diameter 0.1, our K will be 1.5, and our relative roughness is 0.001. So that's our change in head there given flow. Now the next thing we want to find is going to be our our flow given given the delta head. So if we want to write a function for that, our flow, so we're given a delta head, and we also want to provide the lengths, the diameter, the K value, and the relative roughness. And in this, we want to return a resulting flow rate. So how can we find our flow given a change in head? Well, let's look back at our equation. So we want to find Q given a change in head, so we need to find V. But in order to find V, we need to know F. And in order to know F, we need to know Reynolds number, which is rho VD over mu. So we need to find V for that. So we're kind of just going in a loop. So in order to find this, we need to do Newton's method, in which we will give it an equation that's equal to 0. And our equation we want to equal 0 is just Bernoulli's equation. So we'll have our delta head, so our D head, and then plus our heating due to friction over G, and that will equal 0. So that will be our equation that we are bringing to 0. And then we also need an initial guess for our flow in order to find it. And to find our initial flow, we need to find a guess. And we really have no way of knowing what the flow might be, but we can sort of approximate our friction factor. Because if we look at this graph here, we see a graph of friction factor, Reynolds number, and relative roughness. And we have these numbers here. So we can plug in one of these numbers, and that will help us get our Q guess, our guess for our flow. So I'm going to choose 0.01 as my guess. So Q guess is going to equal it will equal so Q, oh my, I'm way over the place. I need to so Q we know equals VA. We know A equals pi d squared over 4. And if we rearrange Bernoulli's equation, we can get that V is going to be equal to the square root of our negative delta head negative delta head times G, come on, times G times 2 over K plus 4 F L over D. Jeez, I'm having trouble with this thing. So that's our V. So our Q guess is going to be this, and we will plug in 0.1. We'll plug in 0.01 for our F value. So let's go ahead and do that. So this will be NP dot square root of our negative delta head times G times 2 divided by 4, or K, plus 4 times F, which is 0.01, times L over D. And then I need to just go ahead, I need to define some of these variables. So D head is going to be equal to just negative 40. K will be equal to 1.5. L will be equal to 5. And then our function that we want to bring to 0, so we have our function, so we have F to 0. Given a flow rate, we want to return our delta head plus our heating friction, or heating due to friction over G. So this, we want to bring back our delta head plus our heating due to friction. So K plus 4 times F comma E D times L over D times V squared over 2 over G. And then we need to solve for V. So just like in our delta head, I can just copy and paste. We need to solve for both V and Reynolds number, so I'm just going to go ahead and copy and paste these down here. Shift enter. Okay, now if we use Newton, which I have to import first, so from scipy dot optimize import Newton. So Newton, our function that we're calling is our f to 0. And our guess, our initial guess is going to be Q guess. Shift enter. There. So that is our flow rate given a change in head. So we can just go ahead and copy and paste this up here. And I want my resulting flow rate to be equal to the Newton equation we just solved. So F to 0, F to 0, wait, I spelled it out. F to 0, comma Q gas. Shift enter. So we can get rid of this. So let's call our function and see what we get. So flow, our delta head was minus 40. Our length was 5, 0.1 for the diameter, 1.5 for K, and 0.001 for the relative roughness. And we should get the same number, and we do. But now what happens if we put a positive flow rate, or a positive delta head? We get an error. It fails to converge. And that's because, well, let's look at this. We have a negative under a radical, and if we're putting a positive delta head in there, it's going to stay negative. So to fix that, we need to take the absolute value. So the absolute value of our delta head is going to be equal to np.abs d head. Okay, and now let's plug it into here. All right, and similarly, we cannot have Reynolds number up here has to always be positive. So to fix that, we want to take the absolute value for V and since delta head, if delta head's negative, Q should be positive because it's going from a higher elevation and higher pressure down to lower, so it's going to be flowing that way. And likewise, if delta head is positive, Q will be negative because it will be flowing down towards the change. So we need to bring back our sign of Q here. Shift enter. And another thing, we can simplify. So this looks an awfully a lot like this. So instead of doing this calculation a second time, we can just return the delta head plus our function p head of Q L D R E D. And again, because if the flow rate is negative, that means we have to take the negative absolute value of our delta head here in order to compensate for that. And then we want to come down here and multiply by our sine of our delta head. So now it should work. Still doesn't work. R is not defined. R. What do I even use R for? I probably forgot an RE. Oh, you are a K. That's why. There. We have a positive delta head, and we have a negative flow. And if I make this a negative delta head, we get a positive flow. So you might be wondering what really was the point of this. It doesn't seem like it really did anything. It kind of just all moved in a circle. Well, basically these are the tools that we'll be using. I haven't even really put in our data yet for our pipes. I haven't constructed our network yet. So these are kind of tools that we will use in functions that we will continuously call on throughout our code that will help us solve for our flows. So let's go ahead and build our pipe network. So our pipes, we're just going to copy that array that we looked at earlier. So from 0 to 1, we have a distance of 1.5 and a k value of 1.5, 0.5, comma 1.5. And from 0 to 2, we will have a length of 2 and a k value of 2. And from 1 to 2, we will have a length of 1.5 and a k value of 0. From 1 to 3, we'll have a length of 1.5 and a k value of 0. So 1, 3, 1.5, 0. From 2 to 4, we will have a length of 0.5, k value of 0. 0.5, 0. And finally, from 3 to 4, 3 to 4, we have a length of 3 and a k value of 2. There, so that's our piping network. The next thing I want to do is I want to state what each row is. So I want to pull this first column because they're my from nodes. So I want to define those. So I want from nodes are going to equal pipes I want the first column. Shift enter. Let's make sure that's right. From nodes. Yeah, okay. Similarly for the two nodes. Pipes. I want the second column. The lengths are going to be the third column. And the K value is going to be the last column. Oh, I messed that up. This should be a 2. There, so that's just defining what all those are. And as you can see, I can pull it, and here are all my from nodes in an array together. The next thing I want to do is define the heights, the elevations for all of my nodes. So the elevation is going to be equal an array, and they are 30 for the 0 node, and then 0 for the rest of them. And now, if I do z from nodes, this should give me the heights for all of the from nodes. So I have an error there, and that is because it wants them to be an integer, but right now they're floating. So to do that, I just change them as type. np.int 32. I'll do the same thing for the two nodes as type. np.int 32. And for my lengths in K, they should be floating points, so they can stay like that. Shift enter. Shift enter, and now it should give me the heights. Yeah, so there. 30, 30 for the 0 nodes, and then 0 for the rest of them. The next thing I'm gonna do is define my external nodes. So my external nodes I know are 0 and 4. So external nodes are going to equal array 0, 4. And I'm going to make those into integers as well. np. And now let's get our pressures, our external pressures that we know. External P, another array. So we know the pressure of 0 is going to be 200,000, and at 4 it will be 0. Shift enter. And now if I, no, that doesn't work. Okay, I thought that might give me, but it doesn't matter. They're both, okay. So now, what else should we do? We can find our total number of pipes. So in pipes, that is going to be equal to the shape of our pipes array, but we only want the columns, so 0. And then that should give us 6. Yeah. And I'm going to, I don't know if, I'll keep it like that for now. And then we also want our total number of nodes. I'm blanking. Nodes. That is going to be the maximum value from these first two rows plus 1 because we're starting at 0. So it's going to be np.max of pipes rows 0 2 plus 1. And if I do in nodes, it should give me 5. Yeah, 5. And then I want to make this into, I want to make this one into an integer. No, it should just be 5. Okay. And the next thing we can do, so we know our we know the diameter of our pipes. So the pipes diameter. Instead of just defining it up here, we can define it, make it cooler, you know, down here. So np.full, and we want our number of pipes, so n pipes, and we want to fill this with our value 0.1. Shift enter, and if I do, should be all 0.1s, yep. And same thing for our relative roughness. np.full and pipes -3. There, 0.001, which was our relative roughness for all those. So there, we defined our pipe system here. So now we can get into solving the flows for all these pipes and all these nodes. So let's define a function that will calculate our flow given the heads of our nodes. And in this, we're going to sorry, I live right across the street from the fire station. So we want to calculate it for all of our pipes. So we need a for loop for I in range. Why is it of n pipes? Let's just do check to make sure it's working. We'll just print I. And then just return, shift enter. Okay. Calc close. It doesn't matter what I put in for the head. We're not even calculating. So it should just print 0 through 5. It's just calc flow. There, yeah. Okay. So how can we calculate our flows in each pipe? So our total flow in each pipe is going to be the head, the delta head. We want to calculate the delta head, right? Yeah, and then if we can calculate the delta head between each pipe, we already have our function up here that will calculate the flow given a delta head. So to do this, our delta head should be equal to the head of the 2 node minus the head of the from node. So our heads 2 node minus the heads of our from nodes. If I print delta head, I need to define my heads first, so heads, can't spell it, heads will be equal, and we make an array for it, np.array of, so we'll just put in some random numbers for our heads, so we'll just start 50, 40, 30, 20, and 10. And let's calculate our flow for the heads. 2 nodes. There. Okay, so those are our delta heads for those. We can make it a little bit nicer if we did. Let's do let me do 2 nodes from nodes and then heads for my 2 nodes. And the heads of my from nodes. And I'm hoping this will give us the 2 node in a column, the from node in a column, the 2 node head, the from node head, and then the delta head. Hopefully. I'll be very sad if it doesn't. Come on. Yes. All right. Oh my god. Okay, so there are the so that's just, we have our, so from node 0 to node 1, we have a change in minus 10, our delta head. So for this, we just calculated the delta head. We need to calculate the flows. So we want to return our flows. I can go ahead and get rid of this. That was just kind of for testing. And to return our flows, we want to start an array for our flows. And we want them all to be 0, and we want the same number of indices in our flows as we do for the number of pipes, because we want that many flows for the pipes. So by doing that, if we do flows equals np dot zeros in pipes, it will give us should give us an array of just 6 zeros. Yeah. Okay. So now that we have our array, our flows are going to be equal to, we also have our delta head, so we can use our function up here. So flows will be equal to our flow function given our delta head, and then the lengths will be lengths I for all of the pipes, the pipe diameters, the K values, and the relative roughness. I am blanking right now. Yeah, it's currently 7:04 p.m. and all I've had to eat today is 4 pieces of bacon. So I'm a little hungry. I can hardly think. Okay. So now if we do this, shift enter. Now with these heads, it should give us 6 flows for our pipes. And it gave us 1 flow for our pipe. That's because this needs to be I. For all the pipes, not just one. That's not right. Why? Why? Yeah, so I'm just gonna be straight up here. I wrote the code out once before this, and it was all right. And then I went to record this earlier. I sort of struggled through it. I was definitely not moving nearly as fast as I was this time. At about an hour 30 minutes into my recording, I just got to this part. That's why I was working so fast for this, because I just did it and I remember and I was fresh on it. And I just got to this part and I encountered the exact same problem here. And I looked at it for a while, could not figure it out, so I had to stop my recordings. I went and compared the code I already had made that was right, that gave me a right answer, to the code I was working on, and it was the exact same pretty much. And even after messing with it and actually making it the exact same, it would not work. And that appears to be the exact thing that is happening now. And I have no idea what is wrong with it. It was the exact same numbers, and I'm not happy now. There's one thing I can think of that might fix it. I don't know if it will. The only reason I know this is because I know it's in the final code. And I am very upset, but I'm going to try it. So, if d head is less than some number, some small number, we just want to return 0. This is the only thing that was different between the two codes, because I hadn't gotten to the point to where I needed to show that, and if this doesn't do it, I don't know what will. And it made it worse. There's gotta be something off, but I don't know what it is. I'm not restarting now. This is like my 5th recording. Last one took me 1 hour and 30 minutes. I don't know where the problem is coming from. Is it from? I'm about to like solve this by hand. 40, 30, 30, 20, 10, 10. Fifty, 50, 1, 2, 3. That's right. So I know the delta head is minus 10 for the first one. Its length is 1.5, k value 1.5. Zero. Why? So it's something wrong with this. This is where it's going wrong. But what? Okay, so my Q guess was right. Is it just like it's still 0. Let's see. Taking the absolute value of it. It's not. Oh my god. Is that it? Now, um, why is it? That one's working. So it works individually, but not in this. So there's something wrong with this. I calculate my delta head, and can I do that? Can I just do, let me do like, delta head. I just want to copy and paste this down. I'm trying to figure out why this is, because everything works like outside of the loop, but as soon as they all go in a loop together, they stop working. And then can I, name I is not defined. Oh, well I can't, okay. I need to like, copy this entire loop. No, I know it calculated the delta heads, right? I already did this. It's calculating them. Why is it keep giving me that? Because look, this delta head is the exact same as this one too. So if that one gave me 0, why is that one not? This is so frustrating. Is it something with this? Oh my god. No. What about? No. Oh my god. It works. If I plug it in manually, it's printing. This is the only thing that I feel like might be wrong. I need to check. After my last video, I triple checked it, and it was pretty much the exact same. Flows in P dot zeros, in range in pipes, delta head, heads, two nodes, I minus heads from nodes I, flows of I equal flow delta head, length, pipe, K. The only thing different between this and the other one is this parentheses right here, and I do not think that will change anything. I can't fix it.